friends, welcome to the 12th lecture in module 3, where we will talk about example problems on chemical risk analysis, we will talk about CEI examples in this lecture. This lecture is in module 3, where our focus is accident modeling, risk assessment and management. In the last lecture we discussed about how to get the CEI value, that is the index value, if we really know some elementary parameters of the chemical or the gas being released. For example, the operational temperature, the boiling point of the chemical or the liquid, then the ERPG values for various levels 1, 2 and 3, and the operational pressure, the atmospheric pressure, and of course, the height of release, etc. So, most importantly, once you substitute these values for a standard equation as expressed in the last lecture, which we use now for the numerical example, you will understand the chemical exposure index value for a specific ERPG level, which is essentially ERPG level 2. So, CEI values are always computed for the ERPG concentration level 2 as advised by the international codes. However, hazard distances can be computed for various ERPG levels varying from 1, 2 and 3. So, one can have different hazard distances. So, essential outcome of chemical exposure or chemical risk analysis should be the index, which is helpful for me to understand the probable hazard created or expected to be created by the chemical release or the toxic release of the chemical. Second could be what is the maximum distance of influence of this released chemical on the society or on the public. So, again there are two ways by which the chemicals can be released. It could be either in the gaseous form or a vapor, it can be also in the liquid form. The moment it is the gaseous form, straight away I can find the airborne quantity using a standard relationship as I explained in the last lecture. Once you know the airborne quantity, one can get the CEI value, and once you know the CEI value for different ERPG levels, you can get the hazard distances. So, it is a straightforward problem as far as gas release is concerned. When you have a liquid release, you need to actually find out what is the airborne quantity of this liquid. So, for that you should know what is the flash value. So, if the flash value exceeds 0.2 of some quantity, let us say the airborne quantity should be exactly equal to the release rate of the liquid, then one can also find out the total airborne quantity should be the airborne quantity of the pool plus the airborne quantity of the vapor or the flash, etc., if it is less than a specific value. Once you know the airborne quantity in total, then one can find out the CEI, then one can find out the hazard distances for different ERPG level concentrations. In the whole exercise, we said yesterday that the release scenario, you have to identify the release scenario. So, one should identify various release scenarios, and for each scenario one should compute the hazard distances and chemical exposure index. Okay. So, the main problem is for a given plant, for a given layout, for a given process layout of a given system, one should be able to identify the different release scenarios, what we call essentially an hazard assessment or hazard identification. And we all agree and understand that the risk assessment essentially starts with hazard identification, then ends in risk management. So, in between the paths are all of different diversions, where we try to find out the influence of the hazardous chemical or the hazardous operation, etc., on the whole issue of controlling risk within the acceptability level, what we call as alarm level. Okay, that is how it is done. So, let us take an example now, a set of examples and see. So, please pay attention to the figure shown on the screen. The figure actually shows basically a vessel or a container which has got a chemical. The container has got a pressure relief valve for emergency releases. It is mounted above the ground and the release from the vessel is taken through a pipeline, what we call as a pipeline connection. The pipeline may have a hole or may rupture a hole, that is different, there is a connection here. The pipeline also has a flange. The pipeline flange is connected to the delivery line system, where the valve is fixed and this valve will be able to control the flow from the vessel to the delivery system and so on. So, now it does also have a pump. The pump has got a specific pipe to be connected further, so that it is pressurized and supplied in a specific line. So, let us look at this particular scenario, and this also has a hole which can be used for excess flow. The pipeline can have a crack, the vessel can have a crack, the relief valve may fail. Let us see what are the different release scenarios or hazard scenarios present in this specific case, and then see how we can handle this problem. So, the scenario selection is an important step in CEI calculation. Now, the scenarios of the pipeline what you just now saw is to be identified for different cases of failure. So, the pipeline need to be identified for different failure scenarios. Alternatively, even the vessel can also fail. Okay. Once we do this, let us try to look at the failure scenarios in sense of rupture. So, rupture could be one cause which can exit out the liquid or the gas in any form. So, rupture of the largest diameter should be the worst scenario. Rupture of the largest diameter process pipeline could be the worst scenario, because pipelines can be of different diameter. Let us look at the largest pipeline diameter. So, once we fix up the diameter of the pipeline, then there are some interesting regulations given by the international authorities to see how this can be analyzed or envisaged as an hazard scenario. For diameter less than 50 millimeter, diameter smaller than 50 mm, we generally consider full bore rupture. For diameter of the pipeline between 50 to 100 mm, rupture may be equal to that of 50 mm diameter pipe. Of course, that is the guideline to identify the rupture of the hole from which, or the diameter of the hole from which the system can be exiting. If you have a diameter greater than 100 mm, then rupture area should be considered. the rupture area should be approximately equal to 20% of the pipe cross section. That is the guideline given. Now, let us apply this concept and see what are the possible failure scenarios for the vessel connected to the pipeline, which is then connected to the process delivery system. Please pay attention to the screen. Now, the screen shows various release scenarios. Let us say the first release scenario could be the failure in the process pipeline. Okay. Now, there could be a possibility that the process pipeline may fail. If the diameter of the pipeline is less than 50 millimeter, then we will take appropriately the value as suggested by the code, we will take it as full bore rupture. If the pipeline diameter is between 50 and 100 mm, then you should consider equivalent rupture of 50 mm diameter pipeline, and so on and so forth. So, one possibility is there could be a rupture in the process pipeline. The other possibility could be the service line may be ruptured. Okay. This is a process line, this is service line, this may be ruptured. It means the hoses which are connected to the pump on the service line can rupture, and that can be a full bore rupture. The third possibility could be the pressure relief devices. For example, in this case the pressure relief valve, which is relieving the pressure, is directly relieving it now to the atmosphere. In such cases, the calculated total release rate at set pressure is very important. It is assumed that all material released is airborne, okay, in such kind of failure scenarios. The fourth failure scenario could be the connection of the pipeline from the vessel at the bottom. So, there can be a rupture based on the largest diameter of the process pipeline, because the process pipeline can have different segments of exit from the vessel. In that case, consider the pipeline with the largest diameter attached to the vessel using pipe criteria as we discussed just now in this case. The next scenario could be there is a overflow hole which is present in the tank, and tank overflows from that or through that and starts spilling. So, that can be another failure scenario, and so on. So, let us quickly see the scenarios once again and understand how they have been done. Let us say one could be the process pipeline rupture, other could be the service line of rupture, the third one could be the pressure relief valve is failed. Therefore, the total quantity of material released from the vessel becomes airborne completely. The fourth could be the pipeline connected to the vessel is ruptured. So, then in that case look for the largest diameter of the pipeline, because that will first cause more worry. Next could be the overflow hole which is used will also start leaking, and tank overflows through this line and starts spilling over, and so on so forth. It is interesting that there is a basic assumption in the whole analysis. The basic assumption is that all release scenarios as we just now discussed are assumed to continue at least for 5 minutes. Duration. That is an idealization as supported by Amendola et al. 1992. There are some guidelines for estimating the amount of material becoming airborne following a release. Once you identify the release, then it is important to quantify how much of them is airborne, of the released material becomes airborne. That is important. So, there are some guidelines. The airborne quantity refers to the total quantity of material entering the atmosphere over time. So, airborne quantity which we call as AQ actually refers to the total quantity of the material entering atmosphere over a period of time. Now, this can be in different form. This can be a direct vapor release, the release into atmosphere can be A in the form of direct vapor. It can also be a liquid. Once I say liquid, then there are two possibilities. It can flash off, it can become a pool. Okay. So, then in that case pool will also have an evaporation. So, one need to work out how much is the quantity which is either getting mixed up in the atmosphere as a direct vapor if the release is in a vapor form. If it is liquid, what is the total airborne quantity which is arising from the flash, which is a fraction of the liquid, and which is coming from the pool evaporation, which is also part of this. So, you can see that this is supported by Chandrasekharan 2010 A. So, interestingly, CEI scenarios consider material to be released both as liquid or vapor. So, variation in CEI with airborne quantity is very interesting, and we should see this figure now on the screen. The screen shows the variation of the CEI value with the airborne quantity. One can see here that the airborne quantity in kg per second for ERPG2 level concentration, which is given by this equation, is plotted on the x axis, whereas the CEI value what you obtain from this equation is plotted on the y axis, and we already said the maximum number is 1000. If it is more than 1000, CEI has to be remained as 1000 itself. We already said that in the last lecture. Okay. One can see here it varies on a log curve, it varies linear. The CEI value keeps on increasing on a log curve linear for increment in airborne quantity in kg per second up to a specific value. Once the airborne quantity comes closer to 1 kg per second in log curve, then onwards the CEI actually becomes unchanged, becomes 1000, that is the maximum value CEI can attain. So, that is the variation of CEI with respect to the airborne quantity, which is an ideal situation. Now, let us take up a problem, let us say example 1. Let us say the release in ammonia, the release is an ammonia release. So, let us say the ammonia is stored in a 12 feet, the data given is like this. Let us say it is stored in a 12 feet diameter by 72 feet long container or a vessel, which is kept or located or installed horizontally. That is the usual practice how the bullets are installed in process industries. It is stored in its own vapor pressure. These are the data given during the hazard analysis. It is stored at ambient temperature, which is equal to in that location 30 degrees Celsius. So, we want to identify the release scenario. We identified, we made an audit study, and let us say the largest liquid line, that exit from the vessel is 2 inches in diameter. So, it is about 50.8 millimeters. The gauge pressure inside the vessel, because it is stored at a specific pressure, which is 1064 kilopascal gauge. Temperature inside the vessel is 30 degrees Celsius, stored in ambient condition. The boiling point of ammonia, which is taken from the chemical engineering handbook, is minus 33.4 degrees Celsius. Liquid density, let us say rho L is 594.5 kg per cubic meter. CPBHP, the constant, is available for ammonia from the handbook, which is 4.01 in 10 power minus 3. Delta H, that is the release height from the tank. We already said the tank is kept horizontal, therefore, the tank is kept this way, and this is of course 72 feet as given in the problem, and the diameter is 12 feet. Okay. So, obviously, the height is going to be actually equal to 12 feet. So, delta H is going to be 12 feet, which is about 3.66 meters. Diameter of the hole, which is 50.8 millimeter, because that is the largest diameter of the pipe which is coming out from the exit of the tank. We already said that here. Molecular weight of ammonia is 17.03. So, step number 1, I have to estimate the liquid release rate. Let us say L. L is given by the equation, if you refer back to the previous lecture, 9.44 10 power minus 7. It is a constant which is converting all those dimensions with respect to the units. So, d square rho L root of 1000 Pg the gauge pressure by rho L plus 9.8 delta H in kg per second, the liquid release rate. So, let us substitute the values 9.44 10 power minus 7, d is 50.8 square, density is 594.5, density is 594.5. So, root of 1000 gauge pressure, that is 164 kilopascal, liquid density 594.5 multiplied by 9.8 into delta H, in this case it is 3.66 meters. So, substitute and do the calculation. I will get L as 61.9 kg per second. That is equation 1 or value 1. So, step number 2 being a liquid release, I would also like to know what is the estimate of flash fraction. So, to estimate the flash fraction, So, I can easily find the flux fraction by the equation given in the last lecture, which is Cp by Hv of operational temperature minus the boiling point temperature, which is going to be 0. Cp by Hv we know it is 4.01 10 power minus 3, therefore 4.01 10 power minus 3. Operation temperature is 30 and this is minus 33.4, that is the boiling point, and which gives me Fv as 0.254. Let us say this is the second value I got. We already know since Fv is greater than 0.2, we should say airborne quantity will be exactly equal to the liquid release rate. So, therefore, the airborne quantity in this particular example becomes 61.9 kg per second. Once I know the airborne quantity for a given problem, I can do step number 3, where I will estimate the chemical exposure index for ERPG2 concentration. So, the ERPG2 concentration for ammonia is 139 milligram per cubic meter. So, therefore, CEI is given by a simple equation which is 655.1 root of AQ by ERPG, in this case 2. So, which is going to be 655.1 root of 61.9 by 139, which gives me CEI as 437. So, step number 4, I want to compute hazard distances. The general equation for hazard distance is 6551 root of AQ by ERPG. If we really wanted to find out for ERPG 1, 2 and 3 separately, one can find hazard distances separately. Let us write down the values for ERPG 2. So, ERPG 2 ammonia value is 139 milligram per cubic meter. ERPG 1, which is taken from chemical engineering handbook, this value is 17 milligram per cubic meter, and ERPG 3 is going to be 696 milligram per cubic meter. So, corresponding hazard distances for ERPG 1, hazard distance for ERPG 2 and hazard distance for ERPG 3 can be computed using this expression as you see above. So, hazard distance for ERPG 2 comes to 4372 meters. Hazard distance for ERPG 1 comes to 12,500 meters, and hazard distance for ERPG 3 comes to 1953 meters. Let us see what is the physical interference of this. For example, let us say this is a release point where the vessel is kept and release is happening, and to this radius hazard distance calculated. The farthest distance is about 12.5 kilometers. So, any person within this range or any person beyond this range will have a different quality of experience of the release. Any person beyond this range will not have any effect of the release at all. Any person between this band will only have a minor sensitization of the release, because there is hazard distance 3, hazard distance 1, and this is of course for 2. So, any person which is closer to this belt in this region will have irreversible effect, but will not be fatal. So, depending upon the qualitative explanation of ERPG 1, 2 and 3 which I explained in the last lecture, one can easily physically interpret and understand the seriousness of the influence or the consequence of the release on the personal safety. That is how it is done in case of any liquid release. Let us take an example of a chlorine release. Let us say a 3/4 inch vapor line is connected, vapor connection is happening, which is connected to a 1 ton chlorine cylinder, stored at ambient temperature is about 30 degrees Celsius. Let us say this cylinder or cylinder connection is fractured. Okay, so cylinder connection is fractured. Please pay attention to the screen now. You can see here the chlorine storage vessel, which is indicated in the figure schematically. It has got a liquid ejection pipe and a gas ejection pipe, and there is a valve bonnet which controls the release of exit from the cylinder, and there are fusible plugs which are also used to seal the cylinder so that no leakage takes place, and there are gas valves. That is the upper gas valve is shown somewhere here, okay, and the lower liquid valve is also there in case because of temperature difference, if the liquid starts releasing from the cylinder, it can be arrested. So, that is the cylinder and that is the scenario what we are going to discuss now. The gauge pressure inside the cylinder is 788.1 kilopascal gauge. The absolute pressure, which is 889.5 kilopascal in gauge. The molecular weight of chlorine is 70.91. The storage temperature is 30 degrees Celsius, stored in ambient temperature. The diameter of the hole of rupture is 3/4 inch, which is 19 millimeter. I want the dimensions in millimeters in this case, and that is the vessel what you see. Let us calculate the airborne quantity. Being a gaseous or a vapor release, it will have no pool vaporization etc. So, step number 1, straight away calculate the airborne quantity. There is no liquid release rate. So, airborne quantity is given by the equation what we saw in the last lecture, 4.751 10 power minus 6 d square Pa molecular weight by T plus 273 to the power half. Let us substitute this 4.751 10 power minus 6, diameter of the rupture is 19 millimeters and the pressure is 888.9 and the molecular weight is about 70.91 and the temperature operation is 30 plus 273, let us say to the power half. Substituting, I get air quality release as 0.74 kg per second, which will remain airborne. Straight away step number 2, one can compute CEI. CEI is given by a simple equation which is 655.1 root of the airborne quantity by ERPG 2 for chlorine. So, ERPG 2 for chlorine concentration is 9 milligram per cubic meter. So, therefore, CEI becomes 188. Once I know CEI, I can compute the hazard distances. So, step number 3, to compute hazard distances, I want ERPG values in level 1, level 2, level 3 for chlorine. Let us see these values. ERPG 2 is 9 milligram per cubic meter, ERPG 1 is 3 milligram per cubic meter, and ERPG 3 is 58 milligram per cubic meter. So, the hazard distances for ERPG 1, 2 and 3 respectively are, for 2 already we know, for 2 it is going to be 1878, because hazard distance can be computed from this equation, which is 6551 root of AQ by ERPG, corresponding levels. Let us substitute for 1, the value is going to be 3254 meters. Let us substitute for ERPG 2 concentration, I get 1878 meters. Let us substitute for concentration 3, which is 58 milligram per cubic meter, then I get hazard distance as 740 meters. One can easily calculate. That is how the hazard distance are calculated for this problem. So, friends, in this lecture we understood how to compute the chemical exposure index for different release scenarios, how to then compute subsequently the hazard distances for the CEI values and ERPG levels available. We have taken up 2 examples where we solved, one for a gaseous release and one for a liquid release. In the liquid release, we estimated the airborne quantity from the flash fraction and from the pool, depending upon the condition for the specific problem. So, chemical engineering handbook is a standard reference which can be useful to estimate or to know about all the basic characteristics which are required for working out this problem for a specific chemical or hazardous material to be released in a given scenario. So, I would urge you to do a sample problem on your own, use the equations and see. If you have difficulties, please post them to the announcement form. Thank you very much.